Okay. The inspiration for this work came last summer when my co-author, Bill, asked me, if you take a picture of a potato and you want to put a skin of an orange on top of it, how would it look? And, well, that's a strange question. I said, no idea, but let's try it. So we did, and that's how we came up with the notion of texture transfer. And along the way, we also came up with an interesting texture synthesis algorithm, and that's the subject of this talk. First, I'll talk about texture synthesis. So what is the goal of texture synthesis? The idea is that we get an input image of some texture, and we want to get other images that look like that same texture. So the assumption here is that somewhere out there in the real world, there exists true infinite texture. And the input image is just a small sample, maybe like a little peephole that you're looking at this grand, big texture. And what we want to do is we just want to get more samples of that texture. That's all. Okay? And so there are several assumptions here, and one of them is that the input image be somehow large enough to capture the essence of this texture. And the challenges here is, of course, that there's tons of different textures. Some textures are purely repeated, like this brick wall here. Some textures are stochastic, like this white noise. But most of the textures fall somewhere in between, like this image of a banana bread, where the holes are more or less structured, but their placement and their orientation and shape very stochastic. And capturing all of this spectrum is the hard problem. So the texture synthesis in graphics, the early works were inspired by texture analysis, the use of image statistics, and also by psychophysics, where people use the filters and filter banks to model what the human eye perceives. And there was a breakthrough paper by Higuerenbergen in '95, SIGGRAPH, and then Dibonnet and Simoncelli and Portilla, and they all worked in this grand fashion. The problem was that the algorithms performed very well on stochastic textures, but not so well on the more structured textures in the spectrum. And that's why my co-author Thomas Leong and I decided to have something completely different, one pixel at a time synthesis algorithm to maybe tackle these more structured textures. And I just recently found out actually that this very similar algorithm was proposed in 1981 as a PhD thesis by Garber, but of course back then the computation was completely infeasible, so it was soon forgotten. So let me talk about Effers and Leung for a little bit to get some background. For me, the inspiration comes from language, and Claude Shannon proposed a way to generate English-looking text using the n-gram model. And for that, we assume that the English text is a Markov model, adheres to the Markov property. Not the right assumption, but let's just go with it. And then what we do is we compute these huge probability tables. For every letter, what's the distribution of every letter given the n-1 previous letters? Okay? Once we have that, to synthesize new text, we just start with some seed words, and then we run this Markov chain, sample from this Markov chain, one letter at a time to get our text. And you can also do this with words instead of letters. So here is an example. Say we start with the seed words we need, and we have a trigram model. So what's the probability, what's a more likely word after the words we need? Well, we need a, we need the, we need to, for example. Okay? Now we shift the context one letter over, one word over, and we look at what follows need to. Need to sleep, need to think, need to eat, for example. Okay, now we shift it again to eat. Now if the text was some French history textbook, then the word cake has very likely, very high probability. So we have just synthesized a simple sentence. And in fact, there was a program from Bell Labs which took the alt singles news group as their training data, and these are some of the pearls that they have generated. I really like the last one. I spent an interesting evening recently with a grain of salt. Perfect. But there is a point to this actually. The global structure of the sentences makes completely no sense, but locally this, the sentences the structure is very well preserved, which is exactly what we need in texture, because texture is defined by having no global structure, only the local one. So this is exactly what we want to do. Now we just want to try this on pixels instead of letters. And this is the Efferson-Leung in one slide. Basically, we have synthesized some pixels on the left already, and now we're ready to synthesize pixel P. Okay? And to synthesize pixel P, we want to compute the probability distribution of that pixel given the neighborhood pixels, because we are assuming, again, a Markov property that it only depends on the neighborhood. So we could, again, compute these huge probability tables, but in the image domain, that just becomes infeasible. So what we do instead is we just go into the input image, and we search it for all the similar neighborhoods that look like the neighborhood we have. And then we take all of these neighborhoods, and that becomes our histogram for P. Okay, now we need to sample from that histogram. Well, the easiest way is to just take one of them in random and stick it into P. Boom, we are done with pixel P. We can move on to the next pixel. Okay? Now, the algorithm is, of course, very simple, but produces surprisingly good results, especially on structured textures, which was the problem of the previous algorithms. And it kind of brings in an interesting non-intuitive point that synthesis is often easier than analysis. But of course, it's very, very slow. So there was a number of papers on optimizations and improvements to the work, Wayne, Levoy, Harrison, Ashitkin, to name a few. But then came along something that it was even simpler, amazingly simple thing, chaos mosaic work by Xu, Gu, and Harisham, where you take the input image and first you just tile it, and then you take random blocks. You take a random block like the red one, and you place it somewhere else randomly. And then you smooth the edges so it looks okay. And then you repeat this over and over again. And what you get is not that bad, considering how simple this is. And in fact, it was used in the lab textures paper last year at SIGGRAPH. So of course, it doesn't really work well on structured textures, but it shouldn't work for these. So our idea was, let's combine this chaos mosaic random block placement with the spatial constraints of Efferson-Leung and try to make it work. And I have to mention that, as usually is the case in research, a lot of people think of the same thing at the same time. So there is the real-time patch-based sampling paper that's going to come out, I think Harry said, in October by Liang et al., which is very similar to our texture synthesis part of our paper. And then, of course, the previous stock image analogy is very similar to our transfer. So here's the idea. The neighborhood pixels are very highly correlated between each other. And the reason, if you look at pixel P, it really has to be white. It doesn't really have a choice. Its freedom has been usurped by the pixels that were synthesized before it, right? There is no really reason to actually sample for it, because it only has one possibility. So the idea is that forget pixels. Let's go to blocks. Okay? Exactly the same idea, but with blocks. Compute the probability of a block given the neighborhood of that block. And of course, it's faster because you synthesize all these pixels within a block all at once. Note that this is not multi-scale, because the input image is still the original high-resolution input image, not a blurred, scaled version of it. Okay? So this is the main slide of the algorithm. We have an input texture. Let's decide on the size of the block that we're going to use. Okay? Now, first thing we do is the chaos mosaic stuff, basically. We take random overlapping blocks from the input texture, just put them randomly, put them on the plane, we get this. Okay? So this is not a great result, but it's a good start. Now we overlap the blocks a little bit. We introduce some mention of an overlap. And so now to choose block B2, we don't just do it randomly. We choose it so that it somehow agrees with block B1 along the area of the overlap. And these are the blocks that were chosen this way. And then when we put them together, we get something that looks quite a bit better. Okay? Well, you can still see the lines between where the blocks are, right? The lines where we put them together. And one solution is to blur the boundary, but we want it to be purist. We wanted to only use the pixels from the original texture. No new pixels, okay? So we decided, why don't we introduce a curvy boundary, a curve for the boundary? And we would use a curve that would minimize the error between the two patches along their overlap. And we get this kind of a jigsaw puzzle image. It's exactly the same blocks, but put in with these curvy boundaries. And when we put it together, amazingly enough, almost all of the artifacts are gone. Right? We haven't introduced any new pixels. It's all the same pixels from the original text, from the original texture. Nothing new. We just did the boundaries a little differently. Let's look at this in slow motion again. We take two patches. We have an overlap between them. If we just do it with a straight line, you see this nasty line, okay? So instead, we take the overlapping regions. We look at the error between the overlapping regions. And the error here is, you know, where it's white, it's high error, where it's black, it's low error. So the idea is that we want to cut, we want to make the cut at the places where the textures agree the most. Because if they agree, then you wouldn't see the cut, right? So we want to have a path, a vertical cut that goes along the black pixels, hopefully. And with dynamic programming, it's pretty easy to do. We put this. Apply this cut to our original patches, and with this snazzy animation, it works. I was really, really surprised when I saw that, actually. So our philosophy, my co-author tells me, is the corrupt professor's algorithm. We plagiarize as much as we can, and then we cover up the evidence. Okay. Incidentally, he's going to be he's joining MIT this fall, so as a professor. So. Let's see if we can use this to put this to use. But actually, the rationale for this is that the texture blocks are by definition correct samples of the texture. So we are okay. We just need to kind of cover up the boundaries to make sure the boundaries are okay. And the algorithm is like this. You know, we pick a size of the block and size of the overlap. We synthesize pixels in the raster order. We search the input texture for the block that satisfies the constraints to the left and above. And you can optimize this, and in fact, it has been done by Liang et al. With fast nearest neighbor searching techniques. And we paste the resulting block back in using this dynamic programming trick. Okay, so here are the results. The input images are on the top. The output images are on the bottom. Some structured and not so structured textures. Here is another set of results. Again, you know, very different structured and non-structured. And some bricks for you. This is Andy Warhol kind of look-alike. These are very, very hard textures, these two, because the blocks are, the texture elements are very big. Here is another one. Now, the apple one is very hard because there are really only two whole apples in the whole image, and yet it's doing an okay job except for this one thing in the middle. Some food, some other textures. Now, there's some problems, so I wouldn't advise you to eat these tomatoes or these olives. I think they came from Chernobyl. But well, it's obvious why it failed. It's the textures are too, the elements are too big. So now we are ready to apply this to texture transfer. Okay? Now that the texture synthesis part works, let's take a texture from one object and paint it onto another object. Okay? And unfortunately, this to do it right requires separating texture and shape, which is, if you ask any vision person, he'll tell you that it's impossible. It's an unsolved problem. And so we are not going to do that. We're going to cheat. Okay? We are going to assume that we can capture shape and we can capture shape by boundary and rough shading. Okay? And then the algorithm, the modification is very simple. We just add another constraint to our algorithm. We add the similarity of the image, of the underlying image at that spot. So for example, there is a picture of my co-author being painted with a rice texture. And the red square is where we're going to place the texture next. And we want not only for the rice at that point to agree with the rice before it, but we also want to agree with a little bit of the nose underneath. Okay? That's all. And here are the results. This is a Parmesan man and a rice man. I hope Bill doesn't know that I'm showing this. Sometimes one iteration is not enough. So like in this potato and orange thing, we have to go with several iterations. We start with big blocks and then go to smaller blocks. and the resulting image is down right. We can do pairs too, or we can do Renaissance sculptures. Now this is hard actually, okay? Because here, so far, here we cannot compare the two images directly, because they are completely different. A Picasso sketch and a photograph of Feynman. And we cannot really do anything with these directly because they are just not in the same space. You can't compare these two media. So we want to make something that we can use to actually put them in the same area that we can do comparisons on them. And so we introduce correspondence maps, which in this case are just a blurred version of the originals, but you can do anything you want. Now we can do the whole algorithm in this correspondence space where we can measure distances normally, and then just for the results we can go back again and use the textures from the originals. So this is again very much like the image analogous paper, and who knows why we thought about this at the same time. And this is the results, and it's an interesting result. I mean, you can see the influence of Picasso right away because Dr. Feynman is no longer smiling. But okay, so the results. Let's compare the results with the previous algorithms for texture synthesis. The input image is on the left, and then we have Simoncelli and Pertilla, and the chaos mosaic work, and the Wei and Levoy work, and then image quilting. The Efrosin-Leong work is not shown here, but it's essentially the same as the image quilting, except it's much slower. Okay, so this is a Brodats texture patch. This is another structured. So of course, for non-structured textures, the differences are not that striking. And this is a homage to Shannon. We take an image of text, and then we synthesize an image of a different gibberish text. And actually, in our results, you can kind of read what it says, and it's quite amusing. You can read it the paper. So to conclude, we quilt together patches of input image. If we do this randomly, we get texture synthesis. If we do this constrained, we get texture transfer. So image quilting uses no filters. It is not multi-scale. It doesn't even do the pixel at a time thing. And it's fast, it's very simple, and the results are not bad. Thank you very much.
We have time for questions.
Hi. In your previous method had the divergence problem. Does that problem have been solved?
Which problem?
Divergence problem.
The divergence problem where it starts to grow garbage. Yep. Well, it hasn't been completely solved, but it's much less evident. It's actually almost non-existent. I've seen that happen once, and I should have brought an image of that. But it virtually disappeared, yes. And the reason is because now you have these blocks. So even if you slip somewhere, you're going to recover because you're pasting a whole big block instead of just one tiny little pixel. Okay?
Thank you. How do you choose the size of the blocks?
User chosen. I firmly believe that only a human can perceive the scale of texture. At least at this point in the texture analysis, the research, there is no way to actually correctly perceive the notion of what scale it is. You know, are we looking, is a brick wall, are we looking at just, is it a brick is the unit of texture, or is it 4 bricks the unit of texture, or a wall of bricks the unit of texture? Only the user knows. So I let the user pick.
At the corners, you have 4 overlapping blocks, and so your error map gets considerably more complex. Do you see artifacts at the corners, so where the quilt patches overlap the most?
The corners are, yeah. The corners are, of course, the bigger problem. And if artifacts happen, and they do happen, and the images in the tomato images, for example, you can see that they usually happen in the corners. Yes. So the corners, maybe something we can do something for the corners.
Part of the motivation for some of the earlier texture synthesis work was to try to understand the sort of information content. How much information did it take to characterize some of the natural textures? So insight do you think this more recent work gives us on that point?
So the only insight of this work, and I hate to say this because I'm really interested in how texture works, but the only insight is that we have no idea why this works. I wish I knew. I was really actually saddened that this simple trick works so well, because I'm a vision person at heart and I would love to know the essence of texture, but this work doesn't bring you any closer to that. It asks more questions than it answers.